the OSI model. It's the Open Systems Interconnect model. It's very important for networking and transmission. And there's 7 layers in the OSI model. So the first layer is the physical layer. It transmits raw bits of data in ones and zeros in the local area, and it's connected through physical connections like hubs and fiber optics. Then layer 2, it's a data link layer, and that operates through a single local area. It's connected by Ethernet to switches, and that transmits those raw bits of data from that physical layer, and it organizes them into frames. And this layer governs like the VLAN and the STP. And then the third layer is the network layer. If you're referring to the TCP/IP, it would be the internet layer, but in this case for the OSI model, it is the network layer. And it's responsible for routing data and the data packets through routes on routers. The IP, ICMP, and the IPsec are governed in the network layer. Then the fourth layer is the transport layer. It's the most reliable layer. It governs the UDP and the TCP. So it checks for errors and makes sure the data was not corrupt in transmission. And it ensures, for at least for the TCP, it ensures that a connection is made. But not for the UDP. It's a little bit different for the UDP. It's faster, it's simpler, but it's not as good at checking errors or reliability. And then, so for layer 5, 6, and 7, that would be like layer 5 is the session, layer 6 is presentation, and then layer 7 is application. So in the TCP/IP model, they merged that into layer 5 and just call it the application layer. But in this case, we've got 5, 6, and 7. So this layer governs the SMTP, HTTP, HTTPS, Telnet, and DNS. So when a user sends an HTTP request to a web server on the network, the HTTP header is added to the data. And that would occur in the application layer. So it sends it down from the application layer to the presentation, and then the session, and then into the transport layer. So it goes into the TCP/UDP layer, where it fragments the data into segments and encapsulates the HTTP and the data and its header into a TCP header. So then the TCP header contains the source port, destination port, and sequence number, and it does the 3-way handshake for the end-to-end reliability. Then it encapsulates the segments. Then it's brought down to the network layer, where it's encapsulated into segments from the transport layer into the network layer. And this time it's encapsulated into an IP header. So the IP header contains the source and destination IP addresses, and then it's then sent down to the data link layer, where a MAC header is added at this layer, and then a source and destination address for the routing devices for the next hop are added to this as it goes through the internet. Then it's encapsulated into frames, and it's sent to the physical layer in raw bits of ones and zeros, where the web server receives the raw bits from the network, and it reverses the process and goes back up these layers and decapsulates them in each layer by removing headers at each level. So after it goes from the physical layer going back up, it'll go up to the data link layer, and then it will decapsulate it, removing the Ethernet header, and then I'll bring it back up to the network layer, and we'll decapsulate the IP, and then up to the transport layer. Then it'll decapsulate that and removes the TCP header, and then I'll go back up to session, presentation, and application. And that completes the OSI model protocol transition. How do you build a small LAN? Well, actually, as a matter of fact, I actually built one in my own office. I had a small office in downtown, about 10 people, so I was able to build my own. And well, first you have to determine and lay out or map out where all your connected devices are going to be located, and then also how many devices are going to be in your network, so you know what kind of switch to get, and like how many computers and printers you're going to have on that, and what devices you're going to be connecting to that network. You'll also need to decide on what router you're going to need. So, and then along with network cables and how long they're going to be. For a small office, your ISP will provide you with a modem. We only had about 8 to 10 people at any given time, and so maybe around 15 connected devices. So we had to use Hawaiian Telcom because the building was wired through them. So we weren't free to use whatever ISP we wanted. So we went ahead and went with Hawaiian Telcom. And then, so I connected the switch to the network devices with an Ethernet cable running through the drop ceiling in the office to devices like the server, computer, printers. And we didn't have a wireless access point, but you would connect your wireless access point to the switch as well. We didn't need one because the office was only 1,500 square foot and an open concept, so there were no attenuation issues. My router had 8 antennas, which was sufficient for good wireless anyway. So we just went ahead and used the antenna on the router for the wireless. And then as far as Ethernet cables, I actually learned how to use one, make one recently, which is kind of fun, using the twisted pair cables and the RJ45 connector. So that was an interesting activity. So when you connect your switch to the router, which will most likely have a hardware firewall built in, so you don't really need to worry about any separate firewalls for, I guess, for small offices and using those types of routers. And then you can you need that to be able to connect to the internet. Then you have to configure the router settings and your Wi-Fi password and security and all that stuff. So never use the built-in password, and always use a strong phrase for extra security, and don't share your password with random people. And it's always good to change your passwords every once in a while, especially when people leave the company. So then after connecting your router to the modem that you got from the ISP, then I guess you're ready to go. I just did the automatic configuration that assigns the IP addresses to the device automatically. And then I set up shared folders for everyone to be able to access the printer, and then drop their printing in certain folders if they need to. And then I just followed the firewall and encryption instructions from the router, which was very specific to that router. So I had to go ahead and use their direction. And then finally just test to see if everything works. And it actually did work. So I was pretty proud of myself for just winging it for the first time building a small LAN. What is Telnet and SSH? Well, Telnet is an older client-based protocol that uses the TCP/IP networks on port 23. It allows a user on one computer to log on to another computer in the same network, and it's considered to be evil because it transmits data in clear text. So anyone can see what you're sending and receiving, so it's really not secure. So a better solution or option is a remote access protocol alternative, which is the SSH, secure shell, because it provides more security and privacy over an unsecured network, and it's encrypted. So then hackers won't be able to see what it is that you're sending and receiving. Okay, symmetric versus asymmetric encryption. So symmetric, it uses same key encryption and password or password phrases to encrypt sensitive documents. So that's not really recommended because it's pretty risky and easy to crack. So you can probably use that for not so sensitive things, and because it's more cost effective and easier to use. But if you've got something sensitive that you don't want a hacker to get into, it would be recommended or urged to use the asymmetric encryption. So it uses both private and public key encryption. So public keys are used to encrypt data, and only the matching private key can be used to decrypt it. So for example, if you and I have public and private key, and you and I want to exchange information, so we would exchange public keys but we would keep our private keys to ourselves and keep it very private. So say if I'm in the cafeteria and I want to send you a sensitive document, since we already exchanged public keys, I can use that public key to encrypt the document and send it over the internet, and nobody can see it, or unless you, whoever has the private key, can decrypt it. So when you receive the document, you can use your private key to unlock the document, but you're the only one that can do that. You're the only one that can decrypt the message. Unless an attacker is able to steal your private key, then they'd be able to read everything, and then you're in trouble. So keep your private keys safe and out of people's hands, and you'll be all right. What's the difference between HTTP and HTTPS? Well, they both govern how data is transmitted between the client and the server, but the difference is security and integrity. So HTTP is plain text, which can be seen and manipulated and tampered with by what the hacker sees, which is just plain text like Guru 99, versus HTTPS, which is a more secure version of the HTTPS and uses asymmetric encryption. So it's encrypted using SSL and TLS, which is secure socket layer and transport layer security, where what they see is just kind of jumbled letters, and they can't really decipher what it is. HTTPS also verifies the identity of the web server. So how do you get a certificate using HTTPS? Well, it's through the certificate authorities. So in the TLS, how it works is TLS is a more secure version of the SSL. So any website using HTTPS is using TLS, which secures communication like emails, for instance, SMTP or IMAP or POP. So SMTP is for sending, IMAP and POP are for receiving. And so they use symmetric and asymmetric encryptions in different phases. So there's the handshake phase. Let's go to the handshake phase to establish connection. Doing a three-way handshake, there's the SYN, SYNAC, and the ACK, where they establish connection. So once the connection is established, the asymmetric encryption is established for the certificate check using the public key, and then later encrypted with the private session key after the key exchange. So then in the encryption phase, once the secret key is established, the client and the server encrypt the data using symmetric encryption to ensure that the data is transmitted and is protected from eavesdropping, like man-in-the-middle attacks. And then authentication verifies that the identities of the client and the server. And then the server presents its certificate to the client, and then the client verifies the certificate's authenticity, and then the session resumes, and it continues until you terminate it. So you don't have to keep going with the handshake every time you want to communicate. So once it's terminated, then you would have to redo the handshake again. But it is ongoing until you do so. It is good for data integrity. So TLS ensures that the data integrity is checked by checksums called MACs, not MAC addresses or MAC computers, but by message authentication codes with the transmitted data to protect sensitive information. So the recipient can verify that their transmitted data has not been altered or tampered with during the transmission. What's a TCP handshake? Well, TCP stands for Transmission Control Protocol. So it's a three-way handshake that I mentioned earlier. So there's different flags that come with the transmission control protocol, which is you've got the SYN, the ACK, the FIN, URGE, PSH, and RST. So like SYN is the synchronization sequence number communications. ACK is acknowledgement, and acknowledging that the packet's been received successfully. Then there's FIN, which is an indicator to end the communication from one side. So that happens both ways. And then URGE is sort of like a high priority urgent packet. So it kind of pushes it up to the top. And then push is to flush and buffer. And then rest is to terminate or reset a connection, sort of like a FIN, but in a different way. So in the TCP, it's a three-way handshake to start a session before any web page can be transferred or email. The client will send a SYN, like we mentioned, a synchronization. So it asks the server, the client sends that to ask the server to start the session. So essentially, hey, let's talk. Then the web server responds with a SYN ACK, which is kind of a combination between the SYN and the ACK, saying that they acknowledge the packet and that they also want a synchronization. So essentially it's like, yeah, I want to talk. Do you want to talk? And then the client responds with an acknowledgement packet initiating or continuing the session to communicate. So the TCP provides high reliability because when the TCP sends a data packet, it expects to receive an acknowledgement from the receiving end. So if the packet is not acknowledged within a certain time frame, then the TCP automatically retransmits. So that's the great thing about the TCP layer, because it's reliable and tries to retransmit until there is a connection. But the TCP also assigns a sequence number to each of the segments so that when it's received, the receiver can arrange the packets in correct order. So it's not like a jumbled message, it's coming in at the right sort of sequence. And then it also controls the flow, which dynamically adjusts the amount of data that's being sent to the receiver. So then the receiver can actually process it and acknowledges or knows the receiver's ability to process it. So that prevents congestion in the message transfer. TCP also includes a checksum in each of the packet headers, so that detects errors during the transmission. So the receiver compares it to the checksum in the packet header. Then if the checksum doesn't match, then the TCP requests retransmission or drops the packet if it finds corruption or errors. So in order to end a TCP session normally, there's other ways you can leave it, but the proper way to close it is a 4-step procedure where the server sends a FIN ACK, and then the client responds with an ACK saying, yeah, I got your message, I hear you, okay. And then the server sends a FIN ACK as well, and then says, okay, I'm done. And then the server, or sorry, the client sends a FIN ACK, sorry. And then the server responds with an ACK ending this session properly. What's the difference between a TCP and a UDP? Well, a TCP is a connection-oriented protocol with a larger packet header, and that ensures reliability and data integrity. So the TCP checks for errors and acknowledges transmissions are successful before transmitting the data between the sender and the receiver. And then it also has flow control to prevent overwhelming the network at the receiver's end. And so then the data is delivered in the correct order and without corruption. If a connection can't be established, TCP then retransmits until a connection is made or the packet is dropped due to errors or corruption. But UDP is kind of the opposite, where UDP is connectionless. It is lightweight and it is efficient, and so it's used usually for like real-time streaming and gaming, where speed and efficiency is more important than reliability. It doesn't establish a dedicated connection, so as you can see on the slide, it's just like kind of a direct request response, versus the TCP has the SYN ACK handshake, three-way handshake, connective acknowledgement. Yeah, it doesn't establish like a dedicated connection before sending the data, and it doesn't have congestion control. So UDP packets are also sent independently, and it doesn't guarantee that the delivery is going to be in order, or it does not provide error checking. TCP is usually used for reliability and data integrity, while UDP is like real-time scenarios like streaming and gaming, where speed and efficiency is more important than reliability. What is DHCP and what information does it provide? Well, DHCP is a dynamic host configuration protocol. So it's a network protocol used to automate the setup process by automatically assigning IP addresses and other configurations in the network to the devices within the network. So it eliminates the need for manual IP configuration, makes it easier for setup. So it assigns IP addresses like subnet masks, default gateways, and DNS server addresses to the devices. What is DNS and what are the different records you can get from DNS? Well, DNS, or domain name system, it's like the internet's phone book. So translating human readable domain names into IP addresses that computers can understand. It's like how we can navigate the web to access websites using familiar names. Instead of trying to figure out what those complex numbers are, we can just type in regular words and it converts it for us, essentially. It provides records to ensure smooth and efficient communication across the internet is basically what it is. And it's how we can access and interact with the internet. It provides different types of records. So a record that associates a domain name with, say, an IP4 address, or then there's this AAA or quadruple A record that associates a domain name with an IP version 6 address. And then say a name server record specifies the authoritative name servers for the domain. And there's pointer records that perform reverse DNS lookups and mapping IP address to a domain name. And then there's also a text record for a verification or authentication. And then there's something called a CNAME. It's a canonical name record, and it maps alias domain names to the true domain name or canonical domain name. So there's also the mail exchange records, and that specifies the mail service responsible for receiving email on behalf of the domain. Iterative DNS and recursive DNS. So iterative DNS is a series of referrals between DNS servers until the query is resolved or it's determined that it's not available. It's like asking directions and being directed to the next person who might know the answer, and then continuing to ask people for those same directions until you get an answer or until you reach the destination. And so when a DNS resolver receives a domain name query, it checks its cache to see if it already knows the answer. If not, then it starts the iterative process by querying the root DNS servers, then the top level domain servers, and then finally the authoritative name servers responsible for that specific domain. So once it reaches the authoritative name server for the domain, it obtains the necessary information like the IP address associated with the domain name and returns it to the client that's asking about it. And then so for recursive DNS, it's a little bit more automatic. Recursive DNS is a way to resolve the domain's names by recursively querying the DNS servers until the IP address is found. It starts the same, I suppose. It enables the user to access the website and the internet by translating the domain name IP into IP addresses. So when a computer or smartphone requests the IP address associated with a domain name, like say youtube.com, it sends a query to the DNS resolver. First, it begins by checking its own cache to see if it's already been there and it was previously resolved. And if the information is not cached, then the resolver starts a recursive process to find the IP address. So the resolver sends queries to the DNS servers, starting with the root DNS server, then the authoritative DNS servers, and then finally the authoritative DNS server finds youtube.com. So each DNS server provides the information to continue the resolution process until the IP or the address for the domain is found. So it's kind of does it more automatically and quickly. Once the resolver obtains the IP address, it caches the information for future use, and when you return to try to find that domain again. MTU versus MSS. So MTU is the maximum transit unit. It's the largest size of a data packet that can be transmitted over a network in a single frame or packet without fragmentation or being broken down into pieces. So it affects the efficiency of the data transmission. So if the MTU is set too high, it can lead to packet fragmentation. It can also cause delays and reduce network performance. If the MTU is set too low, it can result in inefficient use of the network bandwidth. So for example, Ethernet MTU is typically 1500 bytes, and then say IP version 4 has a standard MTU of 576 bytes. And so the MSS is the maximum segment size. So maximum amount of data that can be included in a single TCP segment. So the MSS value is negotiated during the TCP handshake process between two hosts, and the MSS represents the largest amount of payload data that can be sent in a TCP segment without fragmentation. And that's because of the header size and the encapsulation overhead. The MSS value optimizes the TCP performance and avoids packet fragmentation. So it ensures that the TCP segments can be transmitted efficiently over the network without being divided into smaller pieces. So how would you find the IP address on a Windows and a Linux? So for Windows, the command prompt, you would do WinR and then type in CMD and then ipconfig, and then it'll populate, as you can see on the slide. Or you can do the PowerShell, which is win and X, and then you type in get-net IP address. Or in a GUI, you go into the settings and then go into network and internet. And then under network, you'll find the IP address, the subnet mask, and the default gateway. And on a Linux, you just open the terminal and type config or IP ADDR, and it will give you the information.